Now that we have introduced exponential functions with an example and then compared them with quadratic functions for a moment, let's take a step back and think about how they would look generally. How does a general exponential function look like? And so from our example, we can deduce that we have an initial value, right? So in our example, that looked like this: y equals 100 times 2 to the x power. And so we had this initial value of $100, and that is, we are going to call that now C as a general initial value. Then we had our factor of 2 that we constantly then multiplied to however many days we had find the city of Yonkers. So times 2, times 2 again, times 2 again, always doubling every day. Now, if we have a different situation, we might have 3 or 4, or we might have 1.06. So there are different numbers, and therefore we're giving that number the variable a for any growth factor, we will call it, that we have that fits the situation, and then to the power of x, because x is now our running variable. So in our example, it was the days that the fine had been applied, and so so those are the days that we are plugging in, while the situation gives us the general variables of c and a. So they're situation specific, but then the running variable, the independent variable, is x. And so that's how we're getting our formula: y equals c times a to the x, or you have that also here in function format. So again, c is the initial value and a is the growth factor. Now a has to be greater than 0, and we will see the two different examples where we take a look. What about if it's not growing but declining, or we often say decaying? And what does a look like in either situation, whether it's growing or decaying? But it's definitely always going to be greater than 0. Now the first example, we are looking at a compost pile of 27 cubic feet waste that is decaying. So it's getting smaller as time goes on, and that is at a rate of 10% per month. Now let's let Q of t be the volume of the compost in cubic feet, and that is t months since the decay began. So let's write a formula for that, in this case decreasing exponential function. So we have our function Q of t, and our initial value in this case is 27. Now, what is our growth factor, or in this case decay factor? So what we start with is our full compost pile, but then every month 10% are taken away. So that is minus 0.1. And that is applied every month. So whatever our compost pile is, every month it's times 1 minus 0.1. So that is to the t's power, therefore, for all the months that compost pile is sitting there. And therefore, we then get at the end 27 times 0.9 to the t's power. So that was a decay example. Let's take a look at an increase as a growth example. And so let's talk about money there for a moment. So we're starting a new job with an initial value of $36,000 per year. Now each year thereafter, you will receive a 3% raise. So let's say that S of t will be your salary t years after you started your new job. So we again start with our initial value, which is $36,000. Now we want to think about how it's growing. So again, we have the salary, we keep it, but then every year we are growing it by 3%. So that is 0.03. And we get to the t's power, because it's every year that happens. So every year you have your salary, and it gets more and more and more. So our final result will then be 36,000 times 1.03 to the t's power. Let's do an example again in terms of what does that mean if you're for 10 years at the job, what will you earn afterwards? Let's say that will be S of 10. And we're just plugging in 10 for our variable t into our function, 0.03 to the 10th power. And you may use a calculator for that, and we will get approximately $48,380.99. So what does that mean? That means that after 10 years your salary will be that amount of money. So let me write that down. So that means your salary has grown quite a bit and will continue to grow exponentially, and it will grow faster and faster as time goes on. Now let's think about, what if you were ambitious and at some point you would like your money doubled? So you want to earn double the amount and from when you started, and you would like to know how long do you have to stay in your job in order to make that happen. So what do we need to do here? Well, now we know the salary already, so this goes on the left side, our $72,000, and our formula 36,000 1.03 to the t's power, right? Because we don't know when that will happen. That's what we would like to find out. Well, the first step we can do, we know that already. We want to isolate t, and therefore we have to divide by 36,000 on both sides, and we get as a result 2 equals 1.03 to the t's power. Now here's the thing, we actually don't know yet how to get to the t. If the t was in the base and we had an exponent of pi, for instance, we would take the fifth root, for instance. But in this case we don't know, and so that will be something we will discover in the next week and learn about. Those will be the logarithms. So from our two examples we can summarize that the function or exponential function that we wrote originally as f of x equals c times a to the x, we can also write differently by taking into account the percent increase or decrease, and write it as f of x equals our initial value, that doesn't change, but instead of a I'm going to write 1 plus or minus r to the t's power, just like we have. So if you're given the percent increase or decrease, so the percent rate, then we can write it also like that, but most of the time we will stick with the function that we have up there, where we just write it as c times a to the x. So we will learn more about that and in the one of the next videos.